Good evening, everyone. Sounds like somebody I heard before. Good evening, everyone. Welcome to the long-awaited Mycelium event. My name is Johnsara Ruth. I'm co-founder of Parsons Healthy Materials Lab here at Parsons School of Design. So welcome to Parsons, the new school. Woolman Hall. We're so happy to have you here tonight. This is the event where we can ask, what is the role of this crazy fungal network of threads that grows all around us, but we don't see them? What's the role that they play in shaping the future of healthy materials for architecture, design, and construction? Tonight, I'm pleased to say, marks the 6th in the series of the Field to Form events organized by the Architectural League, and the 4th on which we at Healthy Materials Lab have had the pleasure of collaborating. So a little bit about Field to Form. This series is catalyzed in part by LTL's publication, Manual of Biogenic House Sections. The series has a goal of digging into the possibility of scaling the use of biogenic and geogenic materials for construction to address the major issues of our time, from climate change, biodiversity loss, the human health consequences of our current industrialized building systems, and more. Each event in this series brings together experts across the supply chain of a particular origin material. It's a farmer or a cultivator, a manufacturer, an architect, and sometimes a builder. Each an expert in that particular material and their own particular discipline. And they all come to sit on stage for a conversation. And the goal of these discussions is to understand how we can expand the use of these plant and earth-based materials in architecture, design, and construction so that we can indeed ignite new ways forward. We're sick of talking about the fact that this is in the future. This can happen now. And that's what this series is here to say. We ask questions like, what are the intriguing architectural consequences of these materials? What changes must occur in the design process when the scope of a building expands to include the fields and facilities and laboratories that grow its form? What are the hurdles that might be addressed between growing, manufacturing, code, assembly, cost, supply chains, marketing, and perception? The 5 previous From Field to Form events included the first, which was an introduction of many materials, another which focused on stone, on earth, on hemp, on straw, and now mycelium. So on behalf of my colleagues at Parsons Healthy Materials Lab, we're pleased to be in collaboration with the Architectural League of New York to host these lively discussions with all of you. If you haven't seen it already, there's a display of an impressive array of mycelium products curated by the team of material researchers at Healthy Materials Lab and the Dongia Healthy Materials Library. And many of those manufacturers are here tonight, both on the panel and in the audience. So find them. And there are samples of the world's first fungi-based yogurt back here, provided by Nature's Find. I heard it tastes pretty good. Nature's Find is the sister company of Hydify, whose samples I think are also on display here. So just a few, I had some housekeeping here, which I've lost, but I'll try to remember, which is a few housekeeping pieces, which is the bathrooms are in the back of this room. Exits are also back there. There's stairs and elevators. CEUs can be gleaned from, there's a QR code, I think, in the back here. The piece of paper that I seem to have lost listed all of the sponsors for tonight's event, which is not a small feat. Oh, thank you. This program is supported in part by public funds from the New York City Department of Cultural Affairs in partnership with the City Council, and by the New York State Council of the Arts with the support of the Office of the Governor and the New York State Legislature. See, this is very important. And by the Architecture League members. If you would like information about membership, as well as the League's programs and publications, including the online journal Urban Omnibus, you'll find information in the back and also at arcleague.org. Thank you, Zoe. So now I'd like to move on to this program. And I have the great pleasure of co-moderating tonight with my friend and colleague, Mei-Ling Loco, who will give you a really the broad introduction to mycelium tonight. What I'd like to do actually is give you an understanding or provide an understanding about why this is so important for us at Healthy Materials Lab. So I'll try to do that pretty quickly. So we all know that we hear many loud calls about the threats to life on Earth from the changing climate. And while we work to find ways to address this monumental issue of our time through the disciplines of architecture, design, and construction, there is another threat that we have related to the materials of design and construction. Dr. Shauna Swan, who is here, is an environmental and reproductive epidemiologist based here in Mount Sinai, New York. She conducted research for over 20 years, tracking children until they became adults, to reveal how environmental exposure is impacting natural hormonal function in humans. Her study revealed in 2020 shows that sperm counts have plummeted by over 50% over the last 40 years. So if this trend continues, this means that this alarming rate of decline could mean that the human race itself will be unable to reproduce itself in the next 40 years. This is the threat that we focus on at Healthy Materials Lab. Dr. Shauna Swan shows that this dramatic decline in sperm count around the world is due to exposure to endocrine disrupting chemicals found in plastics in our environments. So, for example, phthalates are endocrine disrupting chemicals which make plastics soft, like here in vinyl flooring, or under your feet, actually, in this room, unfortunately. While bisphenols make plastics hard, like that beautiful polycarbonate. Scientists are asking, is there a chance that this decline could lead to the extinction of the human species, perhaps before climate change? It is known that materials in buildings, cities, objects, and furniture are releasing toxic particles that are absorbed into all of our bodies. We do assume that the materials and products we buy have been tested for safety, yet most chemicals commonly used in building and consumer products in the United States are not regulated for their impact on human health or the environment. And there are many products typically used in construction which contain chemicals linked to human disease. Their ingredients impact people in construction, in production, and the people who live with the materials in their homes. So we cannot continue to build with the same materials Western civilization has been developing for over 80 years. At Healthy Materials Lab, we ask, what is a different way forward? How can we design and build healthy buildings today? We address the toxics and climate issue by charting new pathways to design and build healthy buildings. Our design-led research team is made up of an interdisciplinary group of dedicated researchers, faculty, students, and colleagues from a variety of disciplines, working collaboratively towards bringing awareness and change. We look at materials and ingredients through the lens of material health, asking how does it impact health, carbon emissions, social equity, biodiversity, water, soil, ecosystems? Does it produce waste, or is it biodegradable or regenerative? We ask these questions of materials at every stage of their life cycle. Conventional sustainability has sought to reduce impacts, but that's not enough. We need to radically reduce waste, toxicity, and slow climate change. And we can do this through our selection of materials. We need regenerative materials and technologies that support environments, people, and biodiversity, that remediate toxics instead of produce them, sequester carbon instead of emitting, and contribute to local economies. We need to determine which materials must be durable for a long time and which can or should be durable for a shorter length of time. To create a healthy future, we need material ingredients that are inherently benign. So we ask, what are the viable alternatives for a fully regenerative future? Enter mycelium. So tonight we've gathered some leading researchers, cultivators, manufacturers, designers, and architects who see the promise of this normally hidden in the earth, fast-growing network of threads of the magical fungi kingdom. You probably have seen their biographies online, these speakers tonight, so I'll keep this very brief, and I'm sure they'll all tell you a little bit about them. So as cultivators tonight, in some of the Field to Form events, we call them farmers, but tonight we call them cultivators. We have Joshua English, zooming in from San Diego, California, who's co-founder of Oakhamworks Labs, which is growing mycelium to create products with structural load-bearing properties. You can see a sample on the table. Josh is an artist and designer. And his partner in this project, Chris Magwood, here in person, after crossing the border, brave man, from Peterborough, Ontario, Canada, with mycelium samples in tow. It made it through the customs, awesome. Chris is also co-founder and chief climate officer at Oakhamworks and an experienced natural builder and Rocky Mountain Institute's manager of carbon-free buildings. Thanks for coming. Representing the manufacturer portion of this event is Serena Camarere, zooming in from Milan, Italy. She's head of design and sales for Mogu, a company who makes acoustic panels, wall panels, and resilient flooring, samples also on this magnificent table, that are available now. Serena is trained as an industrial designer. And our architect working with mycelium is Chris Maurer, who's here tonight in person, who came in from Cleveland, Ohio. He's founder and principal architect of Red House Studio, a research, environmental justice, and design studio. And so now I'd like to pass it over to Mei-Ling Loco, my co-moderator here, who's also a board member at the Architectural League and an architectural scientist and designer who's worked with mycelium for 17 years? Is that longer? Shorter? Shorter. A long time. Mei-Ling is also assistant professor at Yale University School of Architecture and founder of Willow Technologies, focusing on ecological design, life cycle carbon, and renewable bio-based materials, among many other things. Thank you, and welcome, Mei-Ling.
Thank you, John Sarah, and welcome, everyone. It's lovely to see you tonight. And I think it's 12 years that I've worked with mycelium, enough to be sick of its smell. So this is sort of an architect's voyage into the world of fungi, and so I'm going to describe it in the way that I understand it. So fungi are free living in our soils, in our water, and all fungi begin their lives as spores. They migrate for distances through the air or by grabbing onto other organisms on the way. After locating a favorable environment, they grow a bunch of root-like structures called mycelium. They transfer nutrients through these hyphae, which are sort of feathery filaments, which release enzymes as well as absorb nutrients from their food source. Their cell walls are made of chitin, sort of a structural polysaccharide also found on the exoskeletons of insects and crustaceans. But they grow and develop as a network, finding compatible friends, and they multiply in a variety of ways based on environmental conditions. And the life cycle begins all over again. Most fungi spend the majority of their lives as mycelium, this underground network, while the visible parts that we know and see, the mushrooms, are the fruiting bodies used for spore dispersal. In the last 2 decades, mycelium, this vegetative state of fungi, has gained acceptance and popularity. I'm sure what this is, this line anyway, as an effective biomass to biocomposite technology, feeding on these tightly bound lignin and cellulosic components of biomass and generating this chitin-bound green building material. In the deep past of material systems, fungal organisms have participated in hydrocarbon and carbohydrate material economies. Yet only in the last, I would say, 2 decades has contemporary design explored fungal technologies as a form of modern eco-manufacturing in service to the built environment. The life cycle of all matter in the form of organic systems, including plants, animals, as well as inorganic systems, mineral rock formations, or petrochemicals, has been sustained by the presence and activity of fungi. In the words of British mycologist, if you haven't read his book, Entangled Life, Merlin Sheldrake, what a name, fungi make our worlds and they also unmake them. They are the most widely distributed organisms on the planet, and they've served as a ubiquitous agent in terms of decomposing dead matter and play a major role in enabling living matter to embark onto new conquests. There are over 6 million species of fungi. We only know somewhere between 8 to 10%, and all of them have their particular appetites. This strain, for example, I cannot say that name, not even going to try, but as seen there, was found in the Amazon, and we know that it actually can digest, metabolize polyurethane, those materials found in our insulation, waterproofing, soundproofing, and that take 20 to 30 years to decompose, and that's a conservative estimate. The Aspergillus fungi is known to feed on crude oil and was employed experimentally to clean up the Deepwater Horizon spill in 2010 in the Gulf of Mexico, which was the largest marine spill in the world. In the last 2 decades, we've seen design capitalizing on this conversion of organic lignocellulosic materials from food waste, agricultural waste, invasive species, to generate a whole range of bio-based insulative materials all the way to high-density structural products. And this is a huge opportunity in terms of the fact that when we realize we lose quite a large percentage of everything we grow to feed ourselves. About 40% is lost somewhere between the farm and our plates. And there's a huge diversity of biomass to look to. Not only the big 4, sugar, corn, rice, and wheat, but a whole host of biodiverse materials and crops that are grown as part of our food system. Today's leading mycelium eco-manufacturing company, such as Ecovative, have leveraged mycelium's enormous enzymatic activities to basically develop a pretty robust, time-efficient growth cycle for a whole range of target application. And they have been matching mycelium strains, such as the Ganoderma, to biomass substrates in order to develop high-quality building products. Here you see the mycelium growing in a grow tray, or grow tool, as they call it, over a period of 5 days, after which they're popped out and dried in order to stop mycelial growth. So you could dry it in the sun or put it in your oven for 2 hours. My kitchen knows the smell very well. You can see an up-close video showing, the chitin formed over the surface of these hemp fibers, and that's what it looks like from day 1 to day 6. Ooh, that's awkward, okay. And so a whole range of products, from the lightweight microfoams all the way to molded materials that are non-compressed to compressed, but these form a whole range of medium to high density products. And so this has enabled designers and architects to explore a whole range of architectural possibilities. In one of the more iconic and what was the first large-scale structure using mycelium was developed in 2014 by David Benjamin, who unfortunately couldn't join us tonight, but would have loved to be here in MoMA PS1. But here he uses a steel primary structure to support these mycelium blocks grown with Ecovative. Here in 2017, a team from Karlsruhe, as well as ETH Zurich and Philip Bloch's research group, developed MycoTree, which was sort of a spatial branching structure made of load-bearing mycelium components. And here they only use mycelium and bamboo and develop this sort of digital fabrication molds and complex node geometries. So steel, bamboo have worked with mycelium. Textiles have also been explored. Here we see through the BioKnit project from the group in Newcastle University looking at knitted fabric as a scaffold and a scaling agent to guide the mycelium growth and form a quite bespoke composite. 3 weeks ago, Big came out with I Am Mushroom. That's how we say that. But using plastic, recycled plastic that is 3D printed and sort of mycelium panels infilled. So a lot of spurge in terms of mycelium projects and experimentation. Here through Jesse Desoliv's group in Myco Matters, you can see El Monolito, which is sort of a structural load-bearing application of mycelium as well. Harris Wang's team at Columbia have tried to eliminate the use of any other material, unlike the others, and have found a way to basically keep the brick alive, allowing those bonds to be formed, in this sort of arc-like structure. In my work, we've also looked at mycelium as the in-between material to serve as insulation and make the panels lighter when designing biocomposites, but almost like a Kit Kat. Mycelium is a fantastic collaborator with other types of bioadhesives and biomass fibers. Mogu, Serena is here tonight, as well as Marisa Montalti. They've been working a long time on essentially developing surface patterns and fantastic customization options for high-quality acoustic panels. And here, geometry has very specific performance in terms of sound absorption at different frequencies. Chris, I'm not going to spoil his work, but has done fantastic work through Red House Studio, developing a drop stitch inflatable technology that can be used over and over again and moved easily on site where biomass is available, eliminating the need for costly and unsustainable formwork. Works here tonight as well have developed a proprietary pending mycelium strain to develop structural load-bearing myceliums, essentially interlocking modules as well as highly integrated SIP panels. We've also seen the progress in terms of high-resolution 3D printing with mycelium. Here, Blast Studio uses coffee grounds to create really high-quality furniture and columns. And 3D printing has moved a long way. We've seen mycelium growing on 3D printed substrates like clay or infused with hydrogel, which can essentially form a mycelium ink that can control the design and performance of these 3D printed materials. And so the list goes on and on and on. My fantastic working group at Yale put together a whole list of innovative projects using mycelium, and you can kind of see, after 2017 till today, a huge rise in terms of experimentation and applications of mycelium. And so we've also seen the rise of a new type of distributed infrastructure where we see companies like Ecovative licensing out their strains to companies primarily in Europe and Australia. And they are able to scale and produce mycocomposites closer to sites and other markets beyond the United States. Here, a designer can essentially mill their mold according to whatever they design, and that is formed into their grow tray. And your grow trays can either be done in these factories or you can ship them to those facilities. And they grow in these quiet, mushroom-smelling like factory spaces, very quiet. And essentially grow over the 5 days in these forms to generate a myco product. It's incredible to see how quickly some of their licensees are scaling. For example, Magical Mushrooms, what a fantastic name, has opened 4 facilities in the last few years. And so there's definitely a market and a way forward with scaling. So tonight we're going to discuss many things across the life cycle of mycelium and mycocomposites, from what strains and what substrates are extracted and that people work with, to how do we produce them, what is the carbon footprint, and what are the requirements. It's very much a lab infrastructure. We're going to look at all the options in terms of products that come out of myco production, and what are the possibilities in terms of maintenance and end of life. So we're also thinking about how we might participate in essentially creating a regenerative relationship with fungi to support not just life on Earth, but address this coupled crises that Jansara mentioned of climate change, biodiversity, that ultimately underpin ecological health. So I'll pass this over to our first panelist.
Okay, well, hello everyone, and my name is Chris Magwood. I'm going to start the presentation for OccamWorks, and then my colleague Joshua, who knows way more about this stuff than I do, is going to take over and get technical with you. But I'm going to start off, and I think you're running the slides, correct, Josh?
Yes, sir.
Yeah. So I guess what I want to do in this position of kind of like getting things going is talk to you as a builder. I have a 25-year career in design, build, residential and small commercial buildings. And that whole career arc has been all about learning about and working with natural materials and really trying to take the potential of any given natural material and turn it into something that works in a modern construction context that sort of meets the code requirements and performance requirements and cost requirements and all of that. My beginning was in straw bale construction, and I remain very enthusiastic about that approach and that technology. But it was also really clear after even just a few straw bale buildings that, you know, no one material, no one approach is kind of like the answer that sort of solves it all. And so I kind of quickly turned into what I call a natural materials omnivore. And, you know, you can see some of the things, you know, I think I've played with almost every kind of material that there is out there, from, you know, waste things like used carpet, natural stone. You can see in the middle there, we did a building using big round straw bales as load-bearing columns, hempcrete, used tires, straw bales, clay floors. You can, you know, roll the slide, Joshua. And taking those things and turning them into what I hope are sort of, you know, really beautiful, durable, functional, high-performance buildings. We can roll to the next slide. The particular technologies in these buildings, that's sort of not what we're here to talk about. But what I want to just get across is, like, there's an exciting range. I think people who've come to lots of field to form things probably know that, of different materials. You can flip the slide again. And again, you know, taking these things, this is a building at our local university, Trent University in Peterborough, Ontario, a classroom building. We can roll into the next one. So what I want to talk about a little bit is this project. So we decided, hey, we've learned a lot about a lot of different materials, but what we haven't really addressed is kind of design for disassembly. And so in 2017, we set out to make a fully panelized building in which absolutely every component in the building could be taken off, taken apart, and put back together again with no waste, no need for replacement materials. And to sort of prove this out, we built it at our home base in Peterborough, Ontario. We took it down, we put it up at a design show in Toronto, and then we took it down and we put it up on an owner's site. And so we, as we often do, incorporated lots of different natural building materials, and you can flip the slide. This is what the project looks like when it was set up at its final site. But if we go to the next slide, in the Zero House project, I had been talking with the folks at Ecovative, and we grew some of their mycelium material onto our prefab straw bale wall panels as kind of an exterior insulated sort of sheathing for the building, and was super excited by the potential for that material. In particular, you know, our ability to grow it, you know, in situ on a straw bale wall panel. And so, you know, excited about mycelium, and I think not that long afterwards, there's a picture of me. I get this package in the mail, and it came from somebody in California, and I open it up, and it was this tube. And as soon as I touched that tube, there was like something, all the things, neurons in my brain that get excited about materials just started firing because, clearly it was mycelium because I'd had some experience with the ecovative material, but this was hard. Like the first thing I did with it was like whack it on the table, and then I jumped on it. And I was so amazed by the density and the strength of this material. But also it's really lightweight, and it just had so many possibilities. It came to me in the form of that tube, but right away, my brain went to, this could be anything from something as boring as a door core, because we need really light, strong, durable things to be in the center of a door, to interior partition panels, to load-bearing SIPs. The tubes, if you squeeze them into a bit of a rectangle, could become framing. ICF blocks, like it was just, all of these amazing things. And so, started a relationship with Joshua, who's going to sort of talk to you next and more technically. And you can see in the picture there, some of the, the various forms that he's been able to grow this material into. And so I'm sort of really here as the warm-up act to pass it off to Joshua, who has become both a friend and kind of like a genius hero of mine. His understanding of what's going on with mycelium and his sort of like intuitive sense, and now more than intuitive, sort of scientific sense of what the organism needs to grow and to sort of develop certain characteristics is it never ceases to amaze me. So I'm going to keep my part short, and I'm going to hand it over to Joshua virtually to talk in more detail about his work.
I'm hoping everybody can hear me okay. Yes, as Chris mentioned, a few years ago, I made a mistake in the lab. Actually, I was working as a designer, working in hospitality, designing chairs, benches, beds for hotel rooms. And at a hotel or at a design conference, some friends of mine, we were sitting around kind of lamenting the fact that materials basically suck. Trees get cut down. Concrete is awesome. I love working with it as a material, but we're just really taking from the earth, and everything is kind of in a sad state of affairs when it comes to materiality. So sitting around one day, a friend of mine said, "Hey, have you ever heard of mycelium-based composites?" Well, the truth is, I had heard of mycelium. I've had a lifelong obsession with fungi, and particularly with the decomposers, the polypores, certainly. And I've taken thousands and thousands of photos of mushrooms. And that's a lay term. I refer to them as fungi, the fruiting bodies of fungi, for a couple decades now. Currently, I work as a mycologist at a company, Ohm Foods, M2 Ingredients, and we grow a few 100,000 bags of mushrooms, functional mushrooms, a month. So I had definitely heard of this, but I didn't know that people were making things with them. And so I decided, hey, I'm going to give it a shot. And when I said, hey, I want to try to be the first designer to create a chair out of this material, my friend said, don't even try it. It's not strong enough to hold up the weight of a human, so don't even try this. This was 5 years ago. And I always love a good challenge. Well, I dove into why and how this is working. Why does this organism do this? And as Mei-Ling pointed out, these organisms are not the fruiting bodies. The fruiting bodies is like 1.1% of the organism, and for the most part, these exist as filaments in the wild. That the mycelium is the most incredible structure. The issue comes in trying to grow it in massive scale. This is one of our grow rooms here at M2. Like I said, we grow about 100,000 different bags of these fungi every month. The issues still come, though, because we're monocropping these. Basically, they are prone to infection. In the wild, these things like to share. They want to have succeeding fungi that share and grow in the breaking down and building up of materials in the forests and in our cities and our bodies. But one of the challenges is getting this to grow in a way that is repeatable. Some of our innovation is really trying to dive into how can we not heat, beat, and treat it. Let's live with what the fungus wants to do, and we want to create the ideal conditions. And our patented technology has successfully incorporated a composite material that includes a third phase, a textile reinforcement phase, that lends itself to creating significant amounts of strength. And as you can see here, we can also take disparate parts and during a 5-day growth cycle, grow them together to create larger superstructures. But when we look at these things on a microscopic level, on these slides here, on this slide here, you see the larger filaments there are cotton fibers, and then you see the mycelium hyphal growth through that. And really, what's interesting to me is that diving more into the lifestyles of the fungi, we really deal with a very small subset of the fungal kingdom. Mei Ling had mentioned this, that there are thousands and thousands of these species that we know about, but there are millions that we'll never know about. And there's a very tiny subset of these, the fungal kingdom, that can grow 3 different types of hyphal growth. Those are generative hyphae, which all filamentous fungi grow. There's binding hyphae, which do exactly like it sounds. It binds things together. And then there's skeletal hyphae, which are also do exactly what they sound. They grow kind of a strong skeleton. And these are pretty unique to the polypore and clade. And the trick is to figure out a manufacturing technique that's repeatable, but then also flexible enough to grow into different form factors. And so we've, over the years, have experimented with different ways of growing this material in a fabric formed technique that allows us to get outside of that rigid mold. And it also happens to turn out that eliminating the rigid mold also really facilitates the fungal growth. Fungi are more closely related to humans than they are to plants, and they breathe oxygen and breathe off CO2 like us. So when we put them in rigid molds, their lifestyle has to change a little bit. When we liberate them from the rigid molds, they're able to express their full morphology. Just because a fungus can doesn't mean it will grow certain types of those hyphal growth. And so our research has shown that when we are able to liberate it and give it that full respiratory cycle, the results are pretty striking. This is our very first installation in the wild. It's more of an art piece than it is anything structural, but this is here in downtown in New York City. And we're really proud of this. This is for an insurance company that's been a really great patron for us over the years. And the truth is that there's so much more work to be done. And I think that one of the first PhDs to get a PhD in kind of this mycelium-based composite world, Dr. Elise Elsacker, who was involved in that project at Newcastle, had a really poignant point in her thesis, her dissertation. She said, this is kind of the first time in material science history where we've kind of rushed to commercialization before we've really understood the fundamentals of the science. And what we're trying to do is kind of move past that and kind of go backwards and really make sure we're understanding the implications of what we're doing. Our material, as Chris mentioned, has a really important traits. One is that it's 4 orders of magnitude stiffer than previously known formulations. And like I said, we're trying to just use the mycelium and growing it as is. We're not trying to heat it afterwards other than the normal drying that's necessary to kill the fungus at the end of the growth cycle. We're not trying to add any exogenous plastics or resins to the material. And so our initial compressive strength is about 1 megapascal. And truly at 1 megapascal, as you can see here, the blue line is our stress strain curve versus other formulations have a fairly mushy stress strain curve there. And this is what I think sets our material apart. And the truth is that there's so much more that's needing to be done here. We still need to raise enough funds so that we can go through the full bevy of tensile strength bending tests, looking at more like durability tests, even though in the wild, fungal material is quite hydrophobic. once you've dried it, it now becomes a very strong sponge. And so anecdotally, we've done some two-hour submission tests where in the literature it shows that you can see upwards of 100 to 600% water uptake in a 2-hour submersion test. But our material shows a little bit more promise there with only 20% water uptake after a 2-hour submission test. There's more to come. We're thankfully got the support of the Autodesk residency program. We recently were appointed a space in the Autodesk residency. And so we're looking forward to continuing to work with partners in the field and trying to advance this forward. I think one of the neat things, like Jonsara pointed out, is that we need to look at regenerative solutions here. And I think part of that is also thinking of it in terms of the businesses that we run as well. And thinking regeneratively as businesses means that we need to kind of break down the silo, be working together, sharing information, sharing technology, and working for the planet and not for the bottom line. And I guess I'll leave it there, and then we'll talk more, I guess, at the Q&A. So thank you very much for your attention.
Hello, everyone. This is Serena from Mogu. So I'm gonna share my screen. So very happy to meet you all. And as I said, I'm Serena from Mogu. So we are a company in Italy. We were founded almost 10 years ago. We are gonna celebrate our first 10 years in next year, February. We were founded as a startup with most probably the unique vision of bringing nature closer to people. Back then, the story of Mogu goes that our founder, Maurizio Montalti, has been, I guess, one of the first pioneers in the world, really, about mycelium technology, together back then with Philip Ross and the folks from Innovative. He founded Officina Corpuscoli back then, which was a design art studio, design research studio, and developed mycelium technology with the support of University of Utrecht in the Netherlands. He later joined with some, well, I would say, fellows from Italy to found Mogu and bring this technology up to industrial scale. So the vision was really about, again, bringing nature, and it is still our current mission in this field, is to bring nature closer to people in meeting the needs of everyday life. And that means for us actually partnering with Mycelium, that you now know everything about almost. So partnering with Mycelium, which is a unique living material, but really feels like an alive partner and collaborator in our everyday life, to actually create a biocomposite material that could implement different functions in our design and architecture, and generally the spaces we live by in our everyday life. So we started in Mogu, of course, by investigating the technology. So we investigated something like 150 fungal species with more than 100 different substrates to identify just the right protocol. Of course, there are different protocols to grow different materials. So we are not talking so much of one specific materials when we are speaking about mycelium materials. It's always a family of materials. For me, I was trained as an industrial designer, and I loved materials in my study program in general. And I used to compare the invention of plastic to the invention of mycelium materials. Now, might sound a little bit bold and ambitious as a comparison, but truthfully, actually, it is not one single material. We're really more investigating the potential of a whole new technology. So back then, in the first really 3 years of Mogu, were just R&D and understanding the technology, understanding the specific field in which we wanted to apply the technology, and we found a very good and interesting synergy with interior design. We decided to focus on interior design specifically for many reasons. First of all, well, just also because of the culture background, because we are Italian. We were founded by one designer, but also the other fellows, the other partners of Mogu, they also had a keen interest in design, but also because mycelium ultimately brings functional and aesthetic properties that are quite unique when it comes to bio-based materials. So mycelium materials have a striking thermal insulation value, and that's something it is very well known nowadays. But it also brings very interesting aesthetic features because it can create a very homogeneous texture and very upcycled aesthetics from waste materials. That's the really interesting part of it. So essentially, you could also look at mycelium as a recycling technology in the end. So in the end, we can use mycelium to actually upcycle these materials and turn them into beautiful products. And that was really our key mission at Mogu. How we do that again is how we cooperate with nature. So over the years, we have scaled up our process industrially. So we now have a production capacity of around 300 square meters per week, and we are planning a four per scale up for the next coming months, really. Thanks also to a recent seed day investment round that we got at the beginning of January for 11 million euros. So as I said, we have scaled up, and interestingly to me, it turned out that actually building a technology from mycelium also involved actually bringing other technologies together that were sort of there and adapting them to create a new one. So we could also in a way see it as a kind of recycling technologies from other industries. So from the agricultural field to the farming, to the mushroom farming and the mushroom growing actually field, to the food production chain and so on. There were challenges in scaling up, of course. So from the lab to the pilot scale to the scale up, there has been always challenges. By dealing with nature, you have to learn how to navigate through, let's say, some parameters that nature loves in nature. So imperfections, cooperation with other organisms, as Joshua brilliantly said, normally fungi love to share and also share the food sometimes. So the risk of contaminations, it's a huge problem, of course, in industrial production. But there are many ways to tackle this. And so we learned at Mogu that there are so many things that you cannot directly understand. So whenever, for example, we try a new shape, somehow if it is totally nonsense, but somehow it feels like the mushroom needs to learn the shape sometimes. But we also have investigated many different ways to actually tackle these industrial issues from the product perspective. And that is something specific from Mogu. We have been always very product driven and not so much technology driven. So we developed from our basic technology a collection of acoustic panels, pluma panels, and wall panels, sorry, and flooring products. So we have tried to adapt our technology to different solutions for interior design. The acoustic panels are more like three-dimensional decorative modules that are already on the market since 4 years, actually. The pluma panels are a little bit more an industrialized version, actually, of our first acoustic panels. So the acoustic panels, essentially, we were still growing into a mold, and the mycelium was taking exactly the shape of the mold. While with the pluma panel, we also wanted to overcome actually the rigid mold and actually be able to grow panels in larger boards that we were then able, that we could then form and post-process afterwards. So with the pluma panel, we basically took larger boards of mycelium and investigated the possibility of embossing or impressing a shape through compression into these panels. These panels are also quite a big hit in our product portfolio. They are meant as wall finishing panels with acoustic and thermal insulation panels. They also allow us to they also allowed us to reduce actually production costs and achieve a very competitive pricing against standard PET felt panels. The largest scale that we could reach so far is actually larger than the one you see in the presentation. It's 120 centimeters by 160 centimeters. Sorry, this is in another scale, I know. And we worked a lot also on finishing the product, because truly what maybe it's a little bit different about Mogo is that we provide finished products, and we took also a super important focus on certifying our products according to specific European standards that are mostly necessary for application in public buildings. So the finishing of our product can be natural, like the beautiful raw and imperfect nature of Mycelium products, but we also provide a fire-resistant finishing material. And over the years, we also implemented other versions that might be looking a little bit less innovative and radical compared to the possibilities of Mycelium, but that actually go towards the standardization of Mycelium products. And that is something that, you know, might feel like a compromise, but it is very important in our vision, because as we are introducing a whole new class of materials, and Mycelium materials are very difficult to perceive on the market, a new finishing that makes them look a little bit more neutral and a little bit more standard could facilitate the introduction and uptake on the market of these products. So I think mostly one thing to cite is one of these coating is actually that we just recently developed, is basically made from upcycled fibers. So at Mogo, we are also taking care of actually developing our own coatings, our own products that are sustainable and that can meet our own standards for sustainability. Just as a little bit, of course, taking care of the product is also taking care of the installation systems. And when you over the years, we were able to actually implement these panels and these products in a whole range of projects, from very small scale offices, commercial spaces, to very big events, temporary events, and large project spaces. From our acoustic walls to our ceilings to flooring, providing sustainable solutions in the end for the interior design world. And with this, I think I'm gonna stop here. And
okay, thanks. I'm Chris Maurer. Nice to meet you all. So we've learned a lot about mycelium and how it can grow mushrooms and it can grow materials. And we've looked in a few projects to see, can we do both at the same time? What you're seeing behind me here is mycelium growing in a time lapse. I think that's obligatory to have a time lapse of mycelium. But this is by the artist Lyndon Gledhill that did some really great microscopy on some of this mycelium growing. I'll just let it play for a sec. But moving on, I wanted to define mycotexture before we get into things. And that's basically using fungi to shape the built environment. And there's a easy way of doing that. Basically, you can take the mycelium and pair that with a plant waste, and then you give it time and space to grow, and then you can actually get a couple things from that. You can get mushrooms. This is what we've historically done with the growth of mycelium, is to use it to cultivate mushrooms, and then our mushroom cultivators would normally get rid of that material. A lot of the materials you've been looking at tonight have basically used that material to make things, but not necessarily prioritize the growth of food in the process. And so we had a project in Africa where that was kind of the premise. Can we do both at the same time? Can we make food and housing all at once? And just to jump back a little bit by why we would want to do that, it's because buildings are responsible for 40% of the world's carbon emissions. Concrete, steel, and aluminum alone are responsible for 23% of that, and a lot of that has to do with the raw material resource extraction. And fungi are famously recyclers, and they can actually use circular resources to make materials. Add on top of that the carbon emissions from building materials, and the world is going to double its building stock by 2060 from 2020, basically. So think of every building in the world and then just double that. And that's how much we need to build to house the people that are the population growth that's coming. To put it in terms of New York cities, that's 40 New York cities a New York City every month for the next 40 years. So that's a lot of buildings. So that's spread out throughout the world, of course. That's not just a New York City popping up over in different places, but that's throughout the world. We're going to build that much in the next 40 years. And here are some of that statistics I talked about with concrete, steel, and aluminum being responsible for 23% of the world's carbon emissions. Alternatively, we could actually mine biomass waste that exists on the planet today. There are literally billions of tons of biomass that go to waste every year. In the United States, there's straw that comes from grain farming. In Africa, we're going to look at very soon, there are 400 million tons of encroacher bush that are produced every year that is actually causing desertification, and by harvesting that, we can turn that into biogenic materials. And then, you can see throughout Asia and the Middle East, there are, bagasse and rice straw and date palm farming waste that a lot of times literally just gets burned to get rid of it, and that puts the carbon dioxide directly into the environment. If we can take that material, convert that into both food and housing at the same time, not only are we using it, leveraging that to feed people, but we can be storing carbon dioxide, keeping carbon dioxide that was drawn down by the plant material, converted into a material using fungi, and then store that material to keep it from re-releasing into the environment. And so this is a project we did in Namibia that looked at taking that encroacher bush that I mentioned. Again, 400 million tons of this bush are available to be turned into to different products. And when industry looked at it and said, what can we do with this bush, they decided it's good for nothing except for burning, unfortunately. They can turn it into charcoal, they can turn it into wood pellets and burn that to produce energy, which of course is better than fossil fuels. But if we take that bush and we grind that up into a powder, we can use that to grow gourmet mushrooms, oyster mushrooms that you see growing in that column there. Take those mushrooms to market, feed people, and then what's left over is that fungal mycelium that is binding together that bush. We put it into that blue press that we made there in Namibia, and we can make these building blocks that are similar to the ones that I have here on the table. And if you get a chance to look at it or touch it, you can hear it's a very, very solid material compared to a lot of the materials that you see here. Basically, what we've done is take the materials you see here and put it into a press and compact it, and then you have a structural material that comes from that. So what we did is we made 1,000 of those blocks, and then we built the world's first structural mycelium building. So all of this, the structural walls of this building are made out of those blocks. And you can see here the construction, load-bearing capacity, using those blocks. Here's, again, some more images that talk about that. That's our site in Namibia. Everything was made using shipping containers, the laboratory, the grow facilities, the office, even the oven that we use to bake the materials were all made out of shipping containers. So this can be deployed into different parts of the bush and basically be on-site, not only farms, but manufacturing facilities that can go and transfer out. So the materials themselves are very multi-functional. The density of this is similar to wood at 0.6 grams per cubic centimeter. The mass is 13 kilograms, so that's similar to a concrete block. The compression strength of this of the blocks that we make in Namibia are 6 megapascals. So that's about twice as much as what's required for load-bearing construction for one-story buildings in Namibia. Compressed earth blocks are usually around 3 megapascals, but we've actually made materials similar to this one that you see here in Cleveland, Ohio, that go up to 26 megapascals. So that's similar to reinforced concrete. Very, very, very strong materials that can be made from this. The organic carbon that's stored in this is about 6 kilograms. Sorry, the formatting isn't working so well there, but the gross carbon dioxide equivalency is actually 20 kilograms. So there's more carbon dioxide represented in that block than there is mass itself. But when we net out all of the processes of making these blocks, it's very close to 1 kilogram of CO2 sequestered per kilogram of material made. So every ton of material we make, we actually sequester a ton of carbon dioxide. And you can relate that to concrete, that the concrete industry basically produces a ton of carbon dioxide for every ton of material made. So if you replace this with that, you're talking about a 2-ton swing by replacing the materials. The R value for these 8-inch blocks is around R19. And then here on the right, you see the equations. Basically, we turned 12 tons of bush into 3 tons of mushrooms and 12 tons of building material and stored 12 tons of carbon dioxide. So from this one waste material, we turned that into all of these positive outlets that helps land regenerate by thinning the bush, provides food for people, stores carbon dioxide, which draws down greenhouse gases, and of course provides housing for communities in need, where half the population of Namibia are living in informal settlements. Just in case you don't understand 6 megapascals, we have a very unscientific demonstration here of a standard concrete block in Namibia versus a myco block, and that's my friend Penda there, expertly showing the brittleness of concrete and the ductility of a myco block. We presented this, and this is basically a material versus a material, but we got a lot of people from the Concrete Apologist Association that were saying it's not fair because this was hollow and yours is solid, and we said, well, that you make them hollow, we make them solid. But we acquiesced, and we actually redid the test with solid concrete. And you see the test here. Basically, we get a little bounce from our material. There's a dent in it, there's a crack in it, but it's not like the catastrophic damage that you see there with the concrete block. And from different angles, we had a lot of fun with this. This guy just loves his job. That was probably the funnest day on site for me as well. But yeah, you can see the damage there. And, concrete is very brittle and heavy, things you don't want in seismic activity where buildings are bouncing together and hitting each other, smashing against each other. Materials like this, the mycomaterials are not only very good in compression, but have that lateral stability, which is great too. So moving a little closer to home, we have a project called Biocycler that looks at not making food and materials in the same process, but actually providing remediation services at the same time as making building materials. And with this project, we're literally recycling houses now. So in Cleveland, Ohio, there are thousands of homes that are slated for demolition, very hard hit by the mortgage crisis, a lot of abandoned homes, a lot of blighted communities, and the city struggles to get on top of this to stabilize home values in the area by demolishing a lot of the houses. So we're doing a project where we're actually recycling buildings, and we're looking at the remediation ability of the mycelium as it does this. So we take C&D waste, we compare it with biobinders, and then you get a new material like this. Again, this one was actually made using that C&D waste to make the concrete block. So it wasn't used to grow mushrooms in this case, but some of the materials that we make do grow mushrooms. They use clean substrates. I do. So we're looking again at scaling this up into kind of a developed world scenario where we could be doing prefabbed housing with the 26 megapascals, moving from one-story buildings. This could actually be used to do high-rise construction. It'd be very similar to cross-laminated timber, which is now used to do high-rise construction, similar to concrete superstructures, but it has a very good carbon footprint in the fact that it sequesters CO2 by taking landfill waste that would normally release that CO2 and convert that into building materials that can be structural. The way that the remediation services play out is that there's an enzymatic breakdown that happens when the fungi digest the substrates. So this is taking C&D waste, mycelium grows on it, it secretes enzymes that externally digest that material that it's growing through, and a lot of the enzymes that are produced are able to break down petrochemicals in the built environment, even really difficult ones to break down, like polycyclic aromatic hydrocarbons, which, if you see the ring bond there, are difficult to break down, but these enzymes are expert at doing it. They've been breaking down hydrocarbons for eons, and this is basically ancient trees that have been turned into petrochemicals. If you think of fossil fuels as being ancient living organisms that have been produced into oil and becomes these different products, the same hydrocarbons are in these petrochemicals that have been in the woody material that they're expert at breaking down. When it comes to heavy metals, which is a really big problem in Cleveland where I am, specifically from lead-based paint, that becomes more difficult because you can't break down those molecule chains. They're atomic toxins. So what you want to do there is exactly the opposite, and you create a longer chain from it, a chelation, by pairing it with a material that makes it so that it becomes undigestible or passes through the body very quickly. And you can see the opportunities for post-disaster relief, where you can clean and sort, grow and press and panelize materials. I'm going to move very quickly through space architecture. We're working with NASA right now on a project to actually grow buildings off planet. The main reason is it's very expensive to take materials to destination, and so NASA is looking for ways to grow things at destination. This is animation that shows by using inflatable forms that can fill bioreactors with living organisms, you can actually make bioperformative materials within the cavity of the external shell of the building. Here you see algae growing on Mars. That becomes the substrate for growing the mycelium, and then you get a multifunctional material once those pair together. A detailed section through there that kind of shows that process. And these are, again, inflatable cavities that are basically like little spacesuits for microbes to grow within the shell of the structure to create an insulative layer and a radiation protection layer. We've developed several archetypes working with one of the mission architects for the Apollo missions. And he developed a 500-day mission for Apollo 17 that never came to pass, but is now being considered for the Artemis missions. And we're making materials for Starlab, which is a company making a commercial space station in Columbus, Ohio, including some very interesting furniture designs that take into account microgravity. Hilton Hotels is one of the funders for the Starlab, and so it's going to be kind of a swankier version of the ISS, where you're basically strapped into a sleeping bag strapped to the wall on the ISS. This can be something a little bit more comfortable, and here you see an animation of what it might be like to try and sleep in a bed that's in microgravity. You need a little bit of help. And so what we have are these inflatable structures that are filled with mycelium that produces excess melanin. And we use melanin because that's a very good radiation protection material. And it was actually found at Chernobyl that there was a proliferation of this dark fungus that was growing that was harvesting the radiation from the fallout at Chernobyl. And so we made some materials, we sent them into space, we've tested them, and the materials that we've been able to make using melanin-rich fungi have protection levels far exceeding normal building materials, even including things like aluminum and lead, very lightweight materials that can be grown at destination, which again is a hugely advantageous thing to save money. And you can see here the synthesis of that material turned into an aerogel from a hydrogel that grew this material, which is amongst the best insulating materials in the world. You can get about an R10 per inch, which is orders of magnitude better than even expanded polystyrene, et cetera. And so circling back to all the projects, I just wanted to kind of point out the fact that these are all circular resources. We're taking waste material and converting them into useful materials. In Africa, it's the bush. In Cleveland, it's these abandoned homes. And in space, there's actually this radiation source that is the biggest liability for space travel. But turn that liability on its head, you can actually convert that into biomass and create building materials from that. So that's my last slide. I'll leave it there, and thank you all.
So I was struck because we did the best we could to fit each of our panelists into their slot, the grower, the manufacturer, the builder, the architect. But of course, each of them can do everything. So we heard a little bit about each. But which was fascinating. So thank you all for your presentations. I think maybe we should just dive in and then open up some questions. But Mei Ling, jump in. Yeah.
Yeah, thank you so much, Chris, Serena, for those fantastic, and Joshua, for those fantastic presentations. So maybe let's go back to the origin story. You know, all of you have experimented with a range of mycelium strains. I'm just wondering, what is your philosophy around choosing a strain and why? And also pairing that with the substrates. I mean, Serena, you guys talked about working with 150 strains, over 100 substrates. What did you cycle down to and why? And maybe each of you could answer that very briefly. Joshua, you do this all the time, so I'm sure we'll have a really interesting answer from you.
So in our case, the parameters were really different. Again, we are speaking about, at Mogo, we are now currently mainly using one single protocol for our acoustic and wall production that is made from residues of a combination of two different residues, cotton waste, the very first waste of the cotton yarn filament, and the hemp waste. So the main selection criteria for the substrate were actually based on the availability of the value chain, economical availability, closeness to Italy, of course. Back then, when we started, hemp was not yet a crop that has been widely transformed. Actually, cultivated, yes, but not transformed in Italy as hemp chives. Nowadays it's coming back, so finally we will also have our own hemp from Italy directly and be 100% sourced and produced in Italy, very locally. However, so generally the selection criteria again for the crops were mainly, of course, biological. First of all, compatibility with the fungal strains, the ability of a specific crop to actually provide sufficient nutrients for mycelium. When it comes to fungal species, there were many different there are many different possible selection criteria depending on the specific material that you want to achieve. So if you want to get a very low density thermal insulation material that is also able to resist, have some kind of structural properties, then most probably a fungal species such as Ganoderma is the right choice because it's a very voracious fungus and therefore provides a very high porosity inside the material. In our case, we actually have found a very specific fungal strain that was actually identified in collaboration with a local Italian university. That is a local fungi, and therefore for us it was also a little bit more kind of ethic choice to actually choose a strain that was already locally present, and it felt like a little bit less interfering with the natural environment. But also, actually, these specific fungal strains provide an incredibly homogeneous mycelium, especially when it comes to the surface properties. Probably you have seen the natural velvety piece that is from Mogo. I think you have one on the table. That is pretty striking as a result of the homogeneity when it comes to the feeling and the tactile properties. So for us, it was really a compromise between functional, industrial, and aesthetic properties as well.
Thank you, Serena. Joshua.
Yeah, we had the benefit of being able to follow on the work of Phil Ross and the folks at Ecovative and the folks at Mogu. So we kind of had a little bit of the trail was already blazed for us there. I had settled on the Ganoderma species, specifically Ganoderma lucidum, which is widely known as reishi. It's one of the most commonly cultivated mushrooms in the world, but it's also like Serena said, it's very grows very fast, grows very strong, and when grown in the right conditions, it can grow the 3 types of fungal tissues that are necessary for making really strong composite materials. And I had looked at Pleurotus ostreatus, which is another very fast-growing mushroom, but only grows a single type of hyphal growth. And we had done some comparisons between those, that species and species like it, and the Ganoderma species. We did look at some Ganoderma species that are native to North America, that are kind of the cousins to lucidum, like Ganoderma sessile and Ganoderma sugae. But when we looked at them under micro CT, we noticed that the fungal structures that we're really after, those trimitic species, certainly the Ganoderma lucidum was a top performer in building those structures that we needed. And like most everybody doing things that are trying to do anything in the built environment, we are also very enamored with hemp, the hemp hurd or hemp shive. It's the waste product of the hemp textile processing process, and usually given to cows and pigs and things to poop and pee on, and that's a very ignominious end for such a wonderful carbon storing plant. And what I see in that is that when we talk about trying to store carbon for long amounts of time in the built environment, being able to put that into long-lived building products means that this incredible carbon sequestering factory known as the hemp plant can do its work for a lot longer if we store it in longer building materials. So that is our substratum of choice, and for the same reasons that the folks at Mogu use it for. But certainly there are definitely some great candidates for that. But the research would show as well that there seems to be some mechanical benefit to using hemp over other substrata when you're just growing them directly.
So it's so interesting to hear the like down and dirty words for the names of these species. You know, it was also really great to see each of your presentations and this theme that comes out about what is that substrata, what is the mycelium digesting in order to make the product, and you know, just calling out how many times each of you use the word waste, that it is this big digester, or the waste from the hemp fiber, or the waste of textiles used for Mogu in order to make new materials, which it all sounds so promising, right? I mean, like this material that can digest waste, that doesn't require, you know, even the fact that, did you say that the factory is quiet? That was another kind of key thing. But there must be struggles. There must be, what are the key struggles that to getting mycelium materials products to scale, as opposed to these other products that we're so used to, the plastics or the wood or other plant-based materials that are coming to scale? What are the key kind of challenges for producing products made of mycelium?
Yeah, I'd be happy to start. So I think one of the bigger challenges with this is it takes time for the mycelium to grow. With manufacturing, normally you're going to take a waste, if you're taking waste product, you're going to pair that with just a resin or a glue, and you're going to stamp that into materials, very quickly. You wouldn't want to wait around for the mycelium to grow, and that's one of the reasons why we try and incorporate mushroom cultivation in some of the projects that we're doing. One, because it's great to feed people, but two, if it takes 30 days to get to a full fruition of the mushrooms, that's a pretty short period for an agricultural process. It's a very long process for manufacturing, though. So if you can vertically integrate these two things, and you can wait 30 days to grow your crop and get that to market, and then one day after that turn that into a building material like we can with this, we feel like that's a good way to overcome that obstacle of the amount of time it takes the mycelium to do what glue can do very quickly.
Do you want to add
Well,
to
if
that?
I may actually intervene, I find actually that time is not necessarily an issue in the manufacturing. It has been our perception because we have become, in a way, well, the way manufacturing works today is that manufacturing of products is, of course, separated from the manufacturing of materials for efficiency. But if you compare, like, for example, growing a tree to actually make wood or wood composite, that can take decades, if not centuries.
Yeah.
Or, for example, even if you take linoleum is a widely applied material, and they produce kilometers of it, of this material, and it takes 3 months to actually for the full production cycle. So time essentially is a factor in manufacturing, of course, is a factor of volume and space you need to occupy, put it simply. But it is the beautiful and amazing thing that it actually mycelium technology can do for us, is to allow us to access actually and come in contact with the time of production of materials. That is the really unique thing, because in nature we really do not perceive the time needed to produce a table made of wood, because we take wood for granted in a way, but that wood comes from a plant that has been growing from decades. While with mycelium, you really experience this firsthand in the lab. And so this is my view. So I would like when you maybe it is a factor, especially when you're experimenting with mycelium, so that you need to wait until 3 weeks before the actually results from the lab comes out, and the first prototypes. But it is, once you get industrialized, that is really, again, just something you don't really consider inside. But coming back to the question, I think one of the main challenges really goes into understanding your main collaborator. So once you have chosen the right partner, so Ganoderma or the species that, for example, we use, you have to really learn his way, and remember that it is an alive organism. So sometimes it is also seasonal in the end, even though we grow it in climate chambers and in control chambers, somehow its DNA still feels, the seasonal aspects. And we see it at Mogo, truly, that in autumn we experience a very easy production somehow, while in summer it is a little bit more complicated, because you also have to control better possible contaminations and so on. So you have to really learn to still listen to the fungus, as we say at Mogo, and also possibly even, why not, talk to them and attend to the fungus and to the mycelium as if in true it is an alive collaborator, so you need to care for the products, even in large-scale manufacturing.
Yeah.
Thanks,
And I'd
sir.
like to add on to that too. I think it's a perception issue with the time, because we think that food comes from the grocery store and lumber comes from Home Depot, but no, lumber comes from forests. These things should take decades, if not 100 or plus years to grow, but we're now harvesting them sooner and sooner and sooner. And it is cynical to think that we're going to put more lumber in our built environment and somehow survive this catastrophe of climate crisis that we're facing right now. We need that. When we take that slow growing sequester of CO2 out of the forest, we reduce biodiversity. We need other animals on this planet to grow. We take away vast resources that nature needs, and instead we could use existing farmland without supplanting food supply, use the waste materials that are already being just sent right back up into the atmosphere, and then turn those into building materials. And it really is kind of changing the paradigm. I often say that, I think the future is going to be more Tolkien than Asimov. And I think when we start to kind of get comfortable with these more natural form factors, with seeing things, like Serena said, we can now couple growth with manufacturing and think in terms and see it happening. And I think that's a very powerful motivator, I think. And I'm very heartened by the future. And I think that as architects start to wrap their heads, and industrial designers start to wrap their heads around these different ways to do it, I think it's going to become ubiquity, as opposed to regenerative design shouldn't be kind of like a thing that you do and you're a specialist in it. It should be the norm. And like you said, Joan Sarah, in the beginning, we should start doing this now.
Thank you, Joshua, Serena, Chris. You mentioned the longer view in terms of thinking about the life cycle of fungi relative to other bio-based materials like trees, fast-growing plants. I wonder if you can also talk about one of the big challenges around quality control, because we're sourcing from industries that don't necessarily care the quality their waste ends up in, that you need as a raw material. And given the fact that this is very much sterilized, we're working with a ton of chemicals to kill all other things that could be a source of food, prevent infections. We might also need plastics, even in growing mushrooms, for food. In our rigid trays, if we eliminate the rigid trays, we still need to sterilize the textiles or whatever we're growing with. What do you think the big challenges are, with that in terms of having clean raw materials, and how is that affecting ultimately the carbon that goes into ultimately, the value proposition around these materials?
Yeah, it's a great point. In commercial scale mushroom growing, the dirty little secret is we use so much plastic, single-use plastic, and the idea is how can we use that? So here at M2, we're looking at ways to recycle those single-use plastics into like biofuels, for instance, so that there is no problems there. But I think the future could also hold things like using solar thermal energy to do some of the sterilization that we need. That's one aspect of it. But you bring up a very good point. Quality is important, and so working very closely with farmers and not kind of treating them as second-class citizens in this process, but actually in incorporating them into our decision making. And then I think also embracing newer technologies like micro CT. I think micro CT is going to quickly become the gold standard for quality in these, certainly for biomaterials, because we can not just qualify, but we can quantify the types of growth. I think the engineers and architects would feel much more comfortable if we knew we were doing a repeatable process.
Yeah, I think, when you are as well, like Joshua said, I think definitely there is a value on the quality of the input. To be honest, it also really depends on the process and how you scale up. In our case at Mogo, I must say that we were lucky to find also a fungal species again that has the property of really being very strong in competition. So not really being sensitive. Like, for example, there are other fungus that are much more sensible to contamination. So one thing is there. And the second thing, again, is how you select your crop. So the other founder of Mogo actually has been a very big expert in selecting biomasses for other scopes and other industrial value chains, and valorizing them through other industrial value chain. That is background. And so we basically had these two know-how inside Mogo, one Mycelium technology and the other expert in biomass, and that was really worth for us to be able to actually select the right crop from the beginning, and passing possibly through actually industrial residues. That's more accurate as a word rather than waste, because Truthfully, it would be more interesting to use waste, like for example, food waste and so on, but that's much more complicated to get as a clean input to the process, you know. While if you use industrial residues from, for example, cotton linters from cotton yarning, that's a really selected crop that you can have because it has a specific dimension. It is dirty, but it is only dirty of dust and lignin, which the fungus loves, of course. And that is, but that is also a very good point. For example, hemp cultivation in Italy it used to be always a very important crop. There are the perfect conditions in hemp for hemp cultivation in Italy, from weather to actually the type of crop that they have here in Italy, the genetics and so on. But however, the way of processing of hemp made the hemp shives actually very dirty up until now. Now, finally, it is changing because they are recognizing the value of hemp shives in green building segment for also other application rather than mycelium. So finally, we are getting a first very clean batches of hemp chives also from Italy. But it is, I would say, it's always a factor of the things. And just to say one last bit, because I really truly was inspired by the presentation and generally all the works I see when it goes, into the field, architectural field, and growing mycelium on site. That could be a very huge potential if we could use, crops that were directly taken from, the landfill. For that, we also need to allow some imperfection actually to happen inside our production system. There are different applications. I mean, as Mogo, we are producing and trying to produce, standardized products that have a specific quality control with replicable properties, replicable aesthetics to meet the market. But once here we are actually switching to architecture with mycelium that actually involves products directly grown on site, and therefore it's a little bit more performative and regenerative, literally as a way of doing, then we can maybe try to allow a little bit more naturalness and imperfection, and therefore also of contamination to happen in the product without affecting the structural properties or the technical properties. Mm-hmm. Just an idea.
Thank you, Serena. No, it's a great point. So it's not just the crop, but also where in the process of crop production do we intersect. I remember back in the day, Ecovative was trying to source hemp from upstate New York. And because we had quite an immature hemp industry, it's dirty, the actual chives. And so they were importing it essentially from the Netherlands that has a much more mature hemp industry and the processing which keeps it clean. And so it's also, as you're saying, finding the right partners and the right stage. But it sounds like from a design point of view, even though you're going for beautiful, standardized products, maybe in the future there will be a personality switch, imperfections, and embracing the aesthetics of fungi. Maybe that can be a segue into the designing with mycelium products.
Yeah, we have a lot more questions to ask everybody, but I'm conscious of the time, and if we might want to open it up to some audience questions. We also have MycoWorks producers sitting in the front row, which if you'd like to add anything, we would love to hear. But yeah.
Thank you for the excellent presentations. It's two architectural application questions. The first is, in the same way that reinforcing steel supercharged concrete, I'm just thinking of scaling up because we saw one-story building, fantastic, but has there been investigation into using reinforcing mesh to go taller, stronger, et cetera? And the second is, can you control the growth of mycelium when you stack blocks that they become their own mortar and can actually make a unified surface?
Yeah, so as far as getting to the point where we're doing multi-story buildings, we believe some of unlocking that will be cross-lamination, in the same way that builders are using cross-laminated timber now, where you take virgin lumber and you basically laminate them in different directions. You can do similar things with the mycelium panels. And to your question about can they actually grow into each other and form their own mortar, that's a concept called biowelding, and I think you may have seen that on some of the slides from Oakham, where they'd basically grown these different pieces and they can weld together. We've done that as well with different panels that have made dome structures, and there's a lot of there's some really interesting artwork around the concept of biowelding by David Benjamin, who often works with Ecovative, to create that biowelding aesthetic and function that's really ingenious and interesting about the living materials being able to make their own mortar. It's really cool.
Yeah, and if I could add too, I think a key is to think about prefabrication is kind of going to be the way that we can see some consistency for the built environment, because obviously we don't want these buildings to fall down because from one growth to the next. I mean, in one single block here, you could have genetic differences between this part of the block to this part of the block. And so it's really important to try to find ways to standardize the growth and have quality. And I think incorporating like our material, because of the textile reinforcement phase, lends itself well to replacing steel rebar in a concrete structure, for instance. And so because of its form factor, it's also going to displace a lot of the concrete. So we can reduce concrete, the amount of concrete needed, and then displace completely the steel rebar in say a foundation or a tip-up wall or something like that, and provide some services. I think it's going to just take some creativity in order to integrate it into the built environment for multi-story buildings.
Other questions from the audience? Okay, Paul?
You're tantalizing us with a block and insulative structure. I want to know kind of how much does it cost, and is it available to specify? And I think I know the answer to that. So then I follow that with and it builds on John Sara's question, which is what are the real impediments to making it something that's available on the market? And it kind of also could be addressed to Chris as well.
Yeah, so I'll pass it around, actually. Didn't mean to tantalize, but they're not available for sale right now. Basically, a lot of this is in research and development. We talked about a few different ways of doing this, using construction and demolition waste as a recycling. The work that we're doing in Namibia, we're building structures for folks that are in informal settlements. So it's kind of part of the funding organization, which is a Standard Bank group, who funded a group at MIT called the Center for Bits and Atoms that is working with Red House. The mission of this was to grow food and provide housing for folks in informal settlements. So the process is basically being geared towards that, or put towards that now. So we're not selling those materials, and I think for a long time, when we continue to do that work with MycoHab, when we continue to do work with HANA and some other companies that we're developing around these concepts, we'll firstly make the materials and then build with them ourselves, thinking along the lines of prefabricated structures, and then sell those units before it goes on to becoming a product that we would manufacture. I've never wanted to be a manufacturer per se. I'm an architect. I want to design buildings. I want to make buildings and potentially sell those buildings. But the manufacturing part of that, I think, would be something that, like Ecovative does, we would want to license that out to proper manufacturers, and then they would sell to the Home Depots of the world and the Lowe's to get that into markets. That's kind of a little further down the line, once we've proved this at scale, made several buildings, and kind of gone along that route first.
Yeah, I would say too that we have to remember that, Mogu and Ecovative may be going back 10 years, for a completely new sort of not just product category, but conceptual way of even, imagining products. It's not going to happen, overnight. There's so much R&D that needs doing, and just I think, being involved with Occamworks, so much more investment. I was at Greenbuild last week talking with a drywall manufacturer, and they were working on some new formulation for the paper that goes on their drywall, and he had a budget in the tens of millions of dollars to like refine the paper on the drywall. Occamworks hasn't seen a fraction of that to help invent a whole new product category. So I think, you know, everybody is doing this on real bare bones budgets, and that, you know, it goes at the pace it goes at when you're, you know, starting with that kind of funding.
Yeah, and I think too that MyCoWorks, I think, is the perfect example of kind of embracing robotics and cobotics to bring this forward. Because if we license this to manufacturers, they're not going to necessarily have the capabilities to have clean rooms and things that are necessary to drive this forward. So finding ways to give them turnkey systems that use robotics and kind of embrace the future, but kind of go back to biology. I think that's probably the best trailblazing that I've seen in the last 10 years, is to see this introduction of large-scale robotics in the manufacturing process.
Does anybody from
Yeah,
MyCoWorks
but
want to mention?
if you do want to settle on finishing materials, those are widely available on the market and available in only 6 weeks' times.
You want to comment at all on bringing something to market?
Hi. So what do you want me to comment?
Well, I mean,
on?
So Fred from MyCoWorks has managed to bring a product to market in a way similar to Mogu, in a different product category, in leather.
Yeah, leather-like material. Yes. So we're in different category here of the topic of today. But like Joshua was saying, is that we managed to scale up our process by internalizing entirely our value chain and like controlling everything, and working then with partners that were capable to transform our material into finished goods. So I feel like I have been like listening to you guys, and I really appreciate, and it's like it's fascinating. So I've been like more like listening and breathing your messages, like, and it's great. I really appreciate what the Parsons School like you've been doing tonight, and because it's again you putting the spotlight on this mycelium category, and it's so cool to see so many people here on the front row here and talking about what you're doing, because you're like really we're showing that there is an interest in that category. And so the more we have the Mogu of this world, etc., and the better for everyone.
I think.
Hi. Sorry.
Sorry, we have time for one last question before we're so over time, but there's so many questions. Okay.
It's a short question. I'm an architect, and I'm interested in the practical qualities as a building material. I mean, what are the characteristics? For example, water resistance, insect resistance, of this mycelium blocks, or fire resistance, whatever.
Of course, it's going to be different for all the materials we're talking about here, but the building materials that we've made in Namibia that become the structural members of the building. There are various ways to prevent against insect resistance, or to prevent against vermin, things like insects. You can raise the pH or lower the pH of the growth medium and the product itself, which is going to be basically an insect repellent. The materials are generally fire resistant because of the mycelium. The substrates are generally combustible, but mycelium has the self-extinguishing characteristic to it. So especially with the blocks that I was showing earlier that are 8 inches thick, that would take hours and hours and hours to burn through. So very high fire rating, which is really appropriate for near informal settlements where fires tend to just obliterate the informal settlements because there's no fire-resistant materials in those. So for that application, it's very appropriate. I think you were talking about weather resistance. There we put a mud plastering on the outside of the building. So it's very similar to wood construction. You just want to skin that with a type of material that would be the weather barrier. And I always point to the fact that wood construction can last for centuries if it's protected well, like softwood, timber framed buildings. There's even timbers within the pyramids that are thousands of years old. As long as you protect them from the elements, they'll continue to be structural. So similar construction to softwood timber.
Can you get some material samples? Well, we invite you to please peruse the materials library selection over here on our right. You could ask some of these manufacturers for material samples for sure.
They'll definitely be in the library after this, right?
Oh, good. And we have a donation to the library. That's very exciting. Thank you. Thank you all for coming. It's been really fascinating. I think there's many, many more questions. We are here for a few more minutes if you'd like to talk to any of the panelists one-on-one, and if you'd like to look and touch and feel or smell some of these Mycelium products here on the right, we welcome that too. I also heard that there's some coupons for the world's first fungi yogurt that are over there on the table over there. So thank you for coming to the world of Mycelium. Thank you.
Thank you, Joshua. Thank you, Serena.
Thank you, Serena, Josh. We'll be in touch.
Thank you.
Bye, Chris.
Thank you.